So what we need to prove the third property, yes? Third property. So I repeat it, for any epsilon positive exist finite numbers of eigenvalues such that absolute value is larger than epsilon. Is it clear from this property that the eigenvalues are isolated? Isolated, it means that there exists a neighbor of eigenvalue, of each eigenvalue, which not intersects with other eigenvalue. So, and one remark, I prove Fredholm theory, but this property does not, we don't use Fredholm theory. We use the Riesz theorem, I remind it. By contradiction, let we have infinite many. Let there exist eigenvalues. So if it is not uncountable, I can take countable number, yes? What we can, different eigenvalues. Why it is important? Is it clear that eigenvectors which corresponds to different eigenvalues are linearly independent? Linearly independent. It can be proved by induction, for example. And linear independence of infinite set is the linear independence of any finite subset. So we can construct spaces. So let's EK so let's define these eigenvectors and then construct subspaces x1, xn. It is linear span of the first n eigenvectors. What you can say about these subspaces? They are increasing, yes? They are increasing. And so on, because they are linear independent. Then remember the Riesz theorem. What you can construct from the larger subspace corresponding to the smallest subspace. For any n natural, we can construct vector xn belonging to larger space, and the distance of this element to previous subspace for some fixed epsilon. Epsilon belongs to 0, 1. And this distance is just the, here n minus 1 to the previous subspace, or to the largest. to the smallest. In the larger subspace, you can find vector with the unit norm in the larger subspace, such that the distance to the next space, smallest, smallest, xn minus 1, sorry, to the smallest space. Xn minus 1 is the previous, yes. So in the larger subspace, you can find a vector with the unit norm, and the distance from this vector to this subspace not less than this number. Yes? By contradiction, there a contradiction exists. Exists epsilon positive and exists lambda k such that lambda k, all this, less than 1. Okay? Good. So what you can say about following vectors? Xn belongs to this. So Xn lies in this space. So I can write it in basis. AK, EK, 1 to n. Then consider vector yn, which equals xn divided on lambda n. What you can say about the norm of these elements? Less than 1 over epsilon, yes? Because xn have a unit norm, and all lambda are larger than epsilon.
Why is that closed space?
Why? Y is defined as xn over lambda n. It is a definition of yn. Xn small, large in this space xn. Xn is the linear span of these vectors. So it can be represented as a sum of this vector. Yn, more convenient vector system, it is xn divided on lambda n. But the norm of xn equals to 1, lambda n larger than epsilon, so the norm of yn less than 1 over epsilon. Operator A is compact, so what you can say about this set? This is bounded set. So it's pre-compact. It's pre-compact set. And just now we obtained the contradiction. We show that it is impossible to choose fundamental subsequence. Similar to proof of the lemma 4. Maybe that, yeah. Very similar arguments. Very similar arguments. But I put A EK equals lambda K EK. So how looks like this vector, yn? Yn looks like AN EN divided on lambda n plus other elements. AK EK divided on lambda n, EK equal from 1 to n minus 1. I write first term outside all sum. So AYN looks like what? This is ANEN, yes? This term. And this term looks like can I write it as xn plus some vector z minus 1, which is from xn minus 1. Why? Why we can do so? Because they have the same first term. See, xn, and this is vector ayn have the same first element, first term, an, en. So it's different from xn only on this part. And all this part lies in this vector.
Can you explain how you wrote this one?
I write the first, well, the last term, the index k equal to n, an, plus other. So it is, what is the problem of writing here? And ayn, I know that this is eigenvector with eigenvalue lambda n. So it is multiplicated on lambda n. So the first term looks like it, and other ek multiplicated on lambda k. And it is different from vector xn only on sums which lies in a smaller space. Only linear combinations of ek with numbers k equals 1 to n minus 1. So let's try choose fundamental subsequence. So let's m larger than n, m I used this. Yes. I use this representation. I use this representation. Where lies all these vectors, this which I subscribe? M minus 1 lie of n. And we have an increasing sequence of subspaces. No. Elements which I subscribe lies in xm minus 1. And this lies in xm. But so it is larger than, but here let's check this, correct this. This epsilon is not connected with this epsilon. In Riesz theorem, it's better to write delta with some delta from 0, 1. It's not connected with this epsilon. By Riesz theorem, we find in a larger space vector with unit norm, the distance to the smaller space less, greater or equal to greater than 1 minus delta. It is Riesz theorem. So this distance is not less than 1 minus delta, because this is from xm and this all sum is in xm minus 1. So this distance larger than 1 minus delta. So no fundamental sequence. Contradiction. Contradiction for compactness of operator. So that's all for this theorem. Okay, Schmidt representation. So let A is compact operator in Hilbert space, then A can be written as Ska x k pk where finite, the sum is finite or infinite, it depends, and where is orthonormal basis and orthonormal system. If operator is self-adjoint, then these systems are the same. It's just the Hilbert-Schmidt theorem. But if operator only compact, the systems are different. So let's consider this operator. What we know about this operator? It is compact and self-adjoint. So by Hilbert-Schmidt theorem, there exists phi k orthonormal basis such that A phi k equals lambda k A star A phi k lambda k phi k. So I take the basis which constructed by operator A star A. What we know about this operator? This operator is non-negative, yes? It means that the quadratic form is non-negative. This is, by definition, for any x, A star A x, scalar product with x is not negative. And it is obvious because this is equals to the ax square. So we know that spectrum lies between infimum and supremum of quadratic form of this operator. So all lambda k are positive. So all lambda k are positive. So by definition, sk A is square root of lambda k A star A. Then, because it is basis, what you can do with arbitrary vector x? For any x from H, you can write it in Fourier series, yes? X scalar product phi k, phi k. Then act by operator A. So Ax equals and moreover in this series, in this sum, we can take away all elements for which A phi k equals to 0. Yeah? We can take it away. So here we can write another limit, and but because I don't know for which how many elements phi k has no 0 result. Take away all A phi k equals to 0. We do not need it right in here, yes, because they are 0. But if it is not 0, so for is it clear that it is the same? The corresponding S number is not 0. Because if A phi k equals 0, then from this we immediately obtain that A star A phi k equals to 0. Yes? but it is eigenvector for this operator. So it equals 0 multiplied on phi k. So it is lambda k a star a. But S number is square root. So this is, and the inverse from this. If lambda k is 0, then you immediately obtain that a phi k must be 0. Yeah? Then for this phi k, define psi k as such vector, divided on sk, which are not 0. I can do it. And what we need to check? We need to check that it is an orthonormal system. Let's check it. And this is eigenvector. It is just lambda k of operator a star a, and here finish phi k phi n, divided on skn sna. But they are orthogonal basis. Moreover, it is orthonormal basis. So this is equal to what? Kronecker symbol, delta kn. So it is 0 if k not n, and if k equals to n, it is 1, but here Sn, Sn, Sn square. So it is orthonormal system. So we immediately obtain by substitution this on psi k. I divided on S number and multiplied it on S number. So it is equals to Sk x phi k psi k, but only for such numbers Sk which are not 0, So in this representation we have we don't write the 0 terms. So is it? Yeah, okay. For maximum. I think it is clear that this operator is compact, yes? Because it is bounded kernel, continuous bounded. Moreover, it is self-adjoint operator because kernel is symmetric function, real valued and symmetric function. So this operator is compact and self-adjoint. Due to Hilbert-Schmidt theorem, it has a lot of eigenvectors, eigenvalues, eigenvectors form a basis. So let's try to find it. So if I integrate by t between 0 and x, then maximum is x, yes? Plus integral from x to 1, and here maximum is t. And equals lambda f of x. So we can take a derivative because these functions are differentiable. So this equals to a composed function. This is derivative for this x, and this is derivative for this x. Minus x fx minus because we have low bound. So we see that this is go away. So we can take second derivative. And boundary conditions. We need.
How can you write this plus x of x and minus x of x?
They are reduced. This plus x of x minus x of x.
This is for the second integration, right? X to 1.
This is derivative of this.
No.
But this is derivative over this x, and this is derivative over this x. So there are two terms, and this is only this derivative. And this part reduced. And this is second derivative. So boundary condition. What are the boundary conditions? Let's put anything. Lambda f0 equals to integral from 0, 1 t f t dt. Lambda f of 1 equals integral from lambda f prime 0 is 0 from here, yeah? And lambda f prime 1 equals so I see that I have following boundary conditions. F prime 0 equals 0 and f of 1 equals f prime of 1. Yes, I see on this all results, and I want to find boundary conditions at points, not non-local as integral, but as values at points. So following. So let's try to solve it. So I take away this. We need these calculations. Let's first. Operator is self-adjoint, so eigenvalues are real. So first situation, lambda is positive. If lambda is positive, then it is exponents. Yes? So it is exponents f equals a x square root of lambda plus b exponent minus x squared lambda. Yes? And square root because lambda is, stays with second derivative. So f prime equals 1 over square aex over minus so as f0 at 0 equals to 0 is derivative, I immediately obtain that a equals to b. So it's like hyperbolic cosine. Yes? I can change it on the hyperbolic cosine. Maybe it's better. So fx is a and now this, yes, a equals to derivative f equals a is not 0. A is not 0 because eigenvector is not 0. So this is the same as or maybe but I divided on sign. Divided this equation on hyperbolic sign. Let's substitute hyperbolic cotangents equals to mu. How looks like hyperbolic cotangents? Yes? We only write it for positive arguments. Mu is positive. Mu is positive. It has a 0 in the denominator and a linear function. Of course, we have one root, which you can calculate it only by computer. Asymptotically, you can solve it if you write Taylor expansion of this function. But I think it's better to allow to Wolfram to calculate it. Such number mu 0, and you have this eigenvector, eigenfunction. Yes, by substitution we understand that it is hyperbolic cosine x over square root of lambda. But I changed the 1 over square root of lambda by mu. But of course it is not all eigenvectors because they must form a basis. So another situation, lambda is negative. Then your function fx looks like a cosine x of square minus lambda plus b sine x over square root minus lambda. Yes? So you must find it in the following manner. F prime x equals 1 square root minus lambda a minus sine plus right, b cosine x square root minus lambda. So f prime 0 equals to 0, it means that b is 0. So your functions are cosine, usual cosine. So fx equals a cosine x square root minus lambda. So a cosine 1 square root minus lambda equals minus a sine. Again, make a not 0 because eigenfunction is not 0. So you can write it, let's make a substitution, equals to mu, positive. And I write it, but here I lose this. A divided on minus square root of minus lambda. And here I can write it as minus square root minus lambda equals to tangents. Or you can write it in following form. Here some part of tangents, and here 1 over hyperbola. So you see that you have infinite many eigenvalues, and you can say that mu n tends to what? This is pi, this is 2 pi. So large. Asymptotically, it tends to pi n. So your operator of class SP, named Schatten, with any p larger than n. And if you want to obtain more precise asymptotic for mu n, you again can write the Taylor's presentation of tangents and try to solve. Okay? So mu n tends to Pn, and you have, so this function and this function are orthogonal. And together they form a basis in space. Okay? So let's start with problems concerning with Fredholm theory. I start with the school tasks. The question, for what lambda n and g there exists solution? Let's use Fredholm theory. First theorem, what says for us? There exists solution if and only if G orthogonal to solutions of this equation for a joint homogeneous equation. Is it clear that this operator is self-adjoint? This function is symmetric. This function is symmetric. So we can take homogeneous equation not for a joint operator, but just for the operator A. It is the same. Yes? So let's homogeneous equation. How you can rewrite it? How you can rewrite it? Take it to the right side and decompose sign. Okay? So if you have a solution, of homogeneous equations, what form has this solution? Lambda is constant, this is constant, and this is constant. So what is the solution of homogeneous equation? Linear combination of sine and cosine. So f homogeneous looks like A sine x plus b cosine x. So put this form in this equation. So cosine t A sine t cosine plus b cosine t dt plus the same part with sine. And we know that sine and cosine are linearly independent. So the coefficients between for sine must be equal. And coefficients for cosine must be equal. What you can say about integrals where we have cosine and sine? For what they are equal? 0, because it is up to the constant sine of 2t, yes, of double t, and p is a period. And for cosine square, integral for cosine square equals p over 2, yeah? Up to formula for double argument. The length of interval pi, and so they equal 1 plus cosine 2t over 2. And integral of cosine 2t is 0. So, and for sine the same. For sine square we have the same. Any question? What? Again, why we take this?
No, the line above, one line
Up?
Yeah, this is the two
I just use the school formula for sine x plus t.
Yes, but
Cosine x, sine x cosine t, sine x cosine t. It is just this.
the second term should be cosine x sine t, I think.
Sine x cosine t plus sine t cosine x.
Yes, yes, but second
Oh, I see. This is cosine. Oh, I write the same. Yes, you're right. Cosine and here sine. And here sine. So here sine. Here sine. T and here cosine. Yes, thank you. So when functions are different, they give us 0, yes? When we have a square of functions, it gives us pi over 2. So here coefficient for sine A, here coefficient for sine lambda b p over 2. For cosine, here b equals, look here, sine cosine 0, sine square gives us pi over 2, so lambda a pi over 2. So we have such system on AB. Because equation was homogeneous, this system of linear equations is homogeneous too. So if you want to obtain non-zero solution, A, B not 0, the determinant must be 0. Or you can try to solve it without any determinants, for example. Because A equals lambda B over 2, then you obtain immediately B equals, take this here, lambda square P square over 4B. Yeah? Two situations. Lambda equals plus minus 2 over pi. So B is any. And A equals to what? Plus minus 2 over P, B, P over 2 equals plus minus B. So lambda equals 2 over P, F equals A equals to B, yes? Plus. So A sine x plus B, plus cosine x. And lambda equals minus 2 over pi, F homogeneous equals A sine x minus cosine x. and lambda not equals plus minus 2 over pi, what we have for f home? 0. Because for these numbers the determinant is not 0. So you immediately can give the answer. You immediately can give the answer. For here, there exists unique solution for any g from L to P. Moreover, you can find it. It is a linear combination of g and sine and cosine. You can try to find the solution, this unique solution, as function f equals g of x plus a sine x plus b cosine x. And you can find the precise values for a, b. It's some integrals for g of x with cosine or sine. And if lambda equals to 2 over p, there exists solution for which g? For which g? G must be orthogonal to solution of homogeneous equation. So g orthogonal, what is here? Sine x plus cosine x. Only for these functions you have solutions. One-dimensional defect. And if lambda equals minus 2 over pi, there exists solution for g orthogonal to sine x minus cosine x. How many solutions we have? How many solutions we have? Any linear theory for any equation, differential, integral, matrix, any linear theory says that. How looks like the general solution? It is some partial solution, yes, and the solution of a homogeneous equation. So it is we have one-dimensional solution. Infinitely many, but one-dimensional, because you can. It is just to the kernel. You can add to any solution the element from the kernel of operator. The kernel is not 0, so here number coefficient a is arbitrary. Okay.
But we have minus 2 by pi also. A sine x minus cosine.
Because we have here a like a equals plus minus b.
So should we have 2?
So we write solution in the a sine x plus b cosine x, and if a equals to a b, I can write it outside brackets, but here plus. If a equals to minus b, b equals to minus a. So we take away a outside brackets, so sine minus cosine.
So considering it as a one solution only.
One-dimensional solution. One-dimensional. A is arbitrary number. So it is a one-dimensional solution. So for homogeneous at a linear space, for a non-homogeneous equation, it is f in space. Because we have a partial solution in addition. So you see how it works, but you can solve it without knowing Fredholm theory. But if you know Fredholm theory, you understand what can happen. Yes? So let's consider more difficult equation. It is so-called, what is the main thing here? Main thing here that this kernel is a linear combination of two functions. So it is so-called trivial kernels. It is trivial kernels. When your kernel looks like of this form. linear combination when we have a division of variables and finite sum. For any kernels, you can repeat all these arguments. But what happens if kernel is not trivial? So let's consider another problem, and I want to discuss two ways of the solution. First method we can solve as Fourier method, and second way is the boundary problem method. So let's consider space L2, 0, 1 and consider Fredholm equation. We can make Olympiad problem, for example. KXT. With such symmetric kernel. I don't define it on the line t equals to x because it is a set of zero measures. It doesn't matter on the integral. So find the solution that depends on lambda, on parameter lambda. For example, if lambda equals to 0, you have the unique solution. You see, this is in operator form. It looks like this. Lambda not with identity operator, but with A. So if you divide on lambda, you obtain, for example, 1 over lambda in spectrum or not in spectrum. First problem is simple. Lambda equals to 0, then f equals to g for any. There exists unique solution. For example, sine of 2024 pi x. But for another lambdas. By definition of the kernel, again, you can write integral in two parts. So f of x minus lambda, or not AB, of course, lambda or L2, 0, 1, so integral from 0 to 1, of course. So integral from 0 to 1. When t minus t 1 minus x, ft dt minus lambda. Again, I write operator is self-adjoint again, symmetric. So we write again the homogeneous equation. We write homogeneous equation. Not adjoint, but for the same operator. Because operator is self-adjoint.
So from the kernel we have defined this some question. X1, its value is x1 minus t for t greater than x.
It is a kernel.
It's
It's
given.
given. The problem is to find the solution of this equation, to solve it. X t less than x here. Yes? Take derivative. Okay, the first derivative integral. This is integral for this x. And this is derivative. And this is derivative for this x. Minus, minus, give us plus. Here, plus so you see that this and this gives us 0 together. So we can take second derivative. Let's take second derivative. Here they are not x, we take a derivative. We have only changing of sign, but here not x. The derivative of x equals to 1. So here there are no x. So x f of x plus 1 minus x and boundary conditions. We obtain differential equation second order. We need to find two boundary conditions. From this equation, f of 0 equals 0. And f of 1 this integral gives 0 and this 0. So f1 is 0, 2. So this is just a solution of string equation with fixed ends. It's oscillation of string, homogeneous string, with fixed ends. And this is equation of this oscillation of the string, and this is solution of this equation, green function. This function is just a green function for this. So for this boundary condition, it's easy to see that operator is this operator f2 derivatives is negative. So if you multiplicate it on f and integrate by parts, so f2 f plus lambda integral f square equals to 0, yes? And then integration by parts, and by this boundary condition, the non-integral part take away, go with it 0. Is 0, so minus f square plus lambda f square equals to 0. Can you say me about the sign of lambda? Minus, positive, positive. So lambda is positive. For 0 lambda we know everything. So lambda is positive. So just sine or cosine. In previous, with homework, we need to consider two situations. We have a negative lambda eigenvalue and positive eigenvalue. Here, all eigenvalues are positive because quadratic form is positive. So lambda is positive. So I take away this integral. I think we need it. And f at 0 equals to 0, then b equals to 0. Let us sign. A is not 0, so And you must understand that when you solve the homogeneous equation in operators form, it is for non-zero lambda the same that you solve eigenvalue problem. You find eigenvectors, but lambda is the inverse numbers to the eigenvalues, as it must be. For that, this is, you know that eigenvalues of compact operators tends to the zero. So just these numbers are eigenvalues of this operator. But eigenvectors Fn as sine pi n x, it is a basis, orthogonal basis. But if you want orthonormal basis, it is have normalization 1 over square root of length of 1 of the square root of the half of the length of the interval. Long sentence, yes, but interval is 1 length, the half of interval 1 over 2, and normalization is 1 over square root of the half of the interval. So it is a square root of 2. Sine pi n x. It is a normal basis. And what you can do now, what is Fourier series? You can try to find the solution in Fourier expansion. You can write right side, for example, function g as series, and solution. But this is just why I write this function. It is one function from this family. And for example, if lambda equals to, I take it away. For example, if lambda equals p square, what is the solution of a homogeneous equation? A sine just right side. It is not orthogonal. This is F homogeneous, it is not orthogonal to the right side. So by Fredholm theory, you have no solution. What it means from Fourier method? Let's try to find solution as Fourier expansion. Ek is just these functions. Oh, no, 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 no. It is for these numbers. These are eigenvalues. So we have this. Can you give the analysis of this equation? First, lambda is not coincide with these numbers. So you immediately obtain that A equals you find solutions in terms of Fourier coefficients. Is it clear how I can obtain it? In the right side, I have only one term, one eigenfunction. Here I have a lot of, the coefficients must be the same. So here can be coefficient b with number 20, 24, yes? Only for this a will be not 0. Other a, k must be 0, because here all coefficients are 0 except this. So you obtain the unique solution with this coefficient for this series. Okay? Second, lambda is sum of these numbers, but k is not 2024. Then what is the homogeneous solution? Homogeneous solution, you see, it is f homogeneous here a this with this number k, but this k is not 2024. So this function is orthogonal to this. So you have solution, but it is not unique. Because what happens? If lambda equals to some p pi square k square, then it is 0. And here coefficient is 0. So you can't find ak. In this situation, ak, just ak, any. Any, when k any, k not equals to, oh, not. Yeah, I write correctly. Because look here, if lambda equals pi square chi square, this is 0. So you obtain ak multiplied on 0, and here all coefficients except this coefficient is 0. What you can say about ak? Arbitrary. So ak is arbitrary. But a for k not equals to 2024. For this fixed number, for this one fixed number, lambda can be equals only for one. What you can say about this? One square root over 2 divided on 1 minus p square k square, and here pi square. It is not 0, because we consider situations that k never equals to this. So you have one-dimensional space of solutions. Yes, because ak is arbitrary. And another an with n not equal to k, an not equal to, what you can say about an? This coefficient is not 0 for this n, but here coefficient is 0. So n must be 0. Other numbers are 0. So you see that we have solution, because right side is orthogonal to solution of homogeneous equation, but we have infinite many, precisely one-dimensional space, because this coefficient is arbitrary. This is one fixed coefficient when lambda equals to this. And again, if lambda equals third situation, lambda equals to, what happens here? Lambda equals pi square chi square, but k is just the 2024. Homogeneous solution coincide up to the constant to the right side. This situation. So, no solution. You have no solution. So you can, for example, if operator A is compact and self-adjoint, you can try to find the solution with Fourier expansion. Second method, I think we have time. Second method, I change here the function, for example, because we solve it. X, independent variable. If I take second derivative, the beginning of the solution is the same. I try to find solution with a differential equation. I take two derivatives. What happens? What changes? Second derivative changes, but second derivative is the same. So is 0, yes? So the equation is the same. Equation the same. The second derivative. But what happens with boundary conditions? They changed. F0 at 0, 0 because x 0. I try to find, I don't solve firstly a homogeneous equation and second find the orthogonality. I just solve this equation. This equation. But the second derivative of this equation for the non-zero right side is the same. But f at 0 equals to 1. X at 1 equals to what? To 1, yes? So it equals to 1. Again, try to solve this. From this, f at 0 equals to 0, because it is the general solution of this equation, yes? F at 0 equals to 0 means b equals to 0. And so f is a sine x square root of lambda. And f of y equals to 1, so a multiplied on sine 1 over square root of lambda equals to 1. So we immediately obtain that sine is not 0. Yes? So a equals 1 over sine 1 square root of lambda for 1 over lambda not equals to pi n. So yes? It is not right. This is not right. I write it as yes, because second derivative must.
It's on L2 space.
The same space, in L2, in L2. But something wrong here because the signs F2 derivative. But again, yeah, lambda is positive. Yes, we check it. Lambda is positive, so square root lambda. And as you see, we obtain the same conditions on n, on lambda n, yes? Only for this lambda you can find a. And then your solution f equals to sine square root lambda x over sine square root lambda, lambda not equals to pi square n square. For all this solution you can write. And if lambda equals to p square n square, you immediately obtain from this formula that x is not orthogonal to sine pi n x. It's just in previous right side, in previous problem, when right side was signed, we have a situation when lambda was equal to some number, yes, but we have solution. Because we have such solution of homogeneous equation which is orthogonal to right side. But for this situation, in other function x, it is not orthogonal to sign. It is not orthogonal to basis elements. Okay, is it clear this? It may be short. Boundary conditions, but boundary value problem is possible when you can find values of function g here and solve. But it is, for example, for such equations, we have a differential equation of second order. For example, you can solve it with the variation of constants. Some times ago, it was named as Weil theorem, but now it is a task for the student. What happens? You have operator which is bounded in some Banach space. You know that lambda belongs to the spectrum of operator, but not eigenvalue, not in point spectrum. B is compact operator. Then it is all given. Then lambda belongs to the spectrum of operator A plus B. Weil consider only self-adjoint operators, and it is known that for self-adjoint operators, residual spectrum is empty. So in this situation, the Weil theorem can be formulated in the following form. The compact perturbations preserves continuous spectrum in spectrum. It can change the classification, but the numbers from continuous spectrum belongs to the perturbation, to the spectrum of perturbation. Okay, compact perturbations preserves continuous spectrum. But this theorem is true not only for self-adjoint operators A, for any compact perturbations preserves spectrum which are not point spectrum. The solution about one line length. So it's short. It is short. By contradiction, maybe. So we have inverse operator, yes? So let's So is it clear what I do? Plus b minus b, and for this operator we have inverse by this assumption. So I can take away in writing here the inverse operator. So what you know, this operator is invertible. But this operator, what you can say about this operator? It is bounded, it is compact. Precompact is the set. Operator is compact. It is compact operator. So it is Fredholm operator, I minus compact. Identity minus compact. So for example, second theorem of Fredholm, alternative Fredholm, is valid. What happens in alternative, Fredholm alternative. One situation, if we have solution for any right side, so this operator is bijective. So it is invertible too. It is invertible, so its composition is invertible. Yes? But lambda was in spectrum. It is not invertible. Yes? So the first choice of alternative is not true. Another choice, non-trivial equation for this operator has non-trivial solution. Non-trivial solution. So it is eigenvalue. So non-trivial solution, then this is equals to 0. Yes? So it is eigenvector. So it is eigenvector for this operator. But lambda is not from point spectrum. Contradiction again. Again, contradiction. So our assumption that lambda not in spectrum is not valid. Okay? So let's write some home task. First, let's consider problem for trivial kernel. Trivial kernel and function pi are linearly independent. Then, huh?
Inside integral.
This is kernel function inside the integral. It is given. Then, solution can be found as where is solution of algebraic system. In what space? In what space it all happens? In any space we want, all functions belongs to this space, all integrals exist. Okay, so you can consider it in any Banach space of functions with only one natural assumptions. All functions belong to this space, and all integrals you meet in this problem exist. So for such, if you see our first problem with sine x plus t, you see that we work with algebraic equations, with system of two algebraic equations. So for such kernels, you needn't consider a part homogeneous equation. It is a general equation. It is general solution. You see that it's for non-homogeneous situation. It is a general solution. And a homogeneous solution is without its function g. Because it's easy to see that if you take it to the right side and put this formula for kernel, you immediately obtain that solution is a linear combination of function g and function pi, function p. So you try to solve it in this form, and you obtain immediately the form of this algebraic system. And second, consider, for example, question for what lambda complex G in L to 0 pi, from 0 to pi, there exists solution.